Our next speaker is Rupert Frank from LMU. He's going to talk about the Wehrl entropy problem.
All right.
Please go ahead, Rupert.
Well, thank you very much. It's a great pleasure to be here. Thanks to the organizers for inviting me to be part of this activity in this beautiful scenery. I understand that I'm sort of not in the center of this meeting, so I'll try to explain things slowly. And please don't hesitate to ask questions. If things are unclear, if notations I'm using is not good, either now or later, I'm happy to explain more. I'm trying to present what I'm doing, but I'm on what I'm interested in, and I'm curious to hear your feedback. There will be the second half of the talk will be about things that I don't know how to do, and this is in particular where I would welcome any feedback you might have. The talk is called the Wehrl entropy problem. I explained to you what that is, and it's based on two papers that you can find on the archive. And I mean, a subtitle is sort of theory of coherent states. And so I will oscillate back and forth between known examples of coherent states. I mean, these Glauber coherent states, Bloch coherent states, states that you all know. And then some questions about general families of coherent states, states that work for general groups when we think what should be good coherent states. And I try to give criteria when coherent states are good and when they're not. So you arrive at coherent states not only in quantum theory, but also in signal processing, also in mathematical physics. When you try to justify some approximations, they appear as technical tools, and so coherent states give you an approximation, and usually they are parameters in the game, and in an asymptotic regime where these parameters are either very small or very large, these coherent states give a good approximation. What I'm talking about does not involve asymptotic parameters. Okay, so I'm interested today in this talk in non-asymptotic and universal questions. And the easiest way to present this, and this is also historically the original way that was proposed by Wehrl in the late 70s, is you start with the ordinary Glauber coherent states, right? These are the states that you all have seen. They're parameterized by point in phase space, a position q and a momentum p, and well, there are square integrable functions on the line. These are Gaussians that are centered at q, and their Fourier transform is centered at p. All right? And so you think of these functions sort of like a basis. Actually, I mean, you have more than countably many, so that's what's called overcomplete, but you can think, to first approximation, you think of them as a basis. Okay. And this is reflected in this completeness relation, which is written there. Anyway, what do you do with this? So imagine you have a quantum state, and I remind you, this is just a non-negative trace 1 operator on your Hilbert space, and now you take expectation value in these coherent states. So what do you get? So first of all, you get now a function of two continuous variables, p and q. That function is non-negative, and because of the completeness relation, it integrates to 1. So in other words, you have a probability density now on phase space. All right. And now what Wehrl suggested, well, instead of looking at the true quantum entropy of the state, you know, the trace rho log rho, you consider now the entropy of this classical probability distribution. And so this is what's called the Wehrl entropy, as Wehrl of your quantum state, okay? And Wehrl studied this thing and derived a lot of properties that it has, and he was arguing that in some now asymptotic regimes, this is a good notion of entropy. It is certainly one that in some situations is easier to compute or to approximate or to estimate than the original entropy. Anyway, that's the quantity that we're interested in. This is the Wehrl entropy. And I mean, this was 1979, I think, so there were two papers. The first one, the 1978 papers, Reviews in Modern Physics. That's a long and big paper about entropy. This is long before quantum information theory. I think it might be nice to revisit this paper and the ideas that are in there. I think they might have some consequences even for modern developments. Anyway, one of the questions that was asked in these papers is, we have now this notion of entropy, here it is, and then Wehrl was asking, what's the minimal value this entropy can have? Okay? And Wehrl was not only asking the question, but he was also giving a conjecture. There's a number 1 that comes out. It's independent of h bar, whatever. But the important thing is that the states of minimal Wehrl entropy are the coherent states itself. Okay, so once again, you start with a quantum state, an arbitrary. You make this classical probability distribution, compute its classical entropy, and now you minimize that classical entropy. And the optimizers, that's the assertion or his conjecture, are coherent states themselves. Doesn't matter where the coherent states sit, what P and what Q you have, everything is translation invariant. Anyway, that was a conjecture, and that was proved by Lieb in 1978, and that was really a very, from a mathematical point of view, a very deep result. That used state-of-the-art mathematics, some sharp constant that were only proved a couple of years before, and I think still now, 50 years later, this has not become easier. This is really hard work and uses some deep results. And actually, Lieb only proved part of it because, I mean, what Wehrl said was not only should this be the states of minimal, not only should they have minimal entropy, but everybody who's not a coherent state should have strictly bigger entropy. Okay, and so that was only proved some 10 years later. Now, what I'm stating here is a theorem that appeared last year, where so it's 3 things that I think are remarkable about this theorem. So number 1, it's an easier proof than these previous proofs that we had. In the deepest thing that I'm using is what's called the isoperimetric inequality, right? So in the plane, you have a set, and that set has an area and a perimeter, length of the boundary, and you say, under given volume, what's the minimal length of the boundary? Well, that is when the set is a circle. That's the deepest thing that I'm using. It's really quite simple, but even more, I mean, there are more important things than that. Secondly, you know, for the Wehrl entropy, the function you're basing is the rho log rho. That's the important thing. But actually, what I'm showing here is the only thing that matters is that function f of the classical probability density that you're taking is a concave function. So that's the only property of x log x that you're using. So in particular, if you like Renyi entropies, or if you're inside a proof and you're bothered by the fact that x log x has a second derivative that does something funny at x equal to 0, then you might smoothen out things. You know, that's what one does in applications, and you have still the same bound independent of all approximations that you're doing. And the third thing is that I'm also able to characterize the cases of equality in this general setting. You know, the thing that for the rho log rho took a long time and that was not known before in the general case. So that's one of these things. And there will be another aspect of this theorem that I'm going to talk about later. Let's go one step further in this Wehrl problem, right? So we said that states of minimal Wehrl entropy are coherent states. Good. Now, how about you have a state that has almost minimal Wehrl entropy? Do we know that this state is almost a coherent state? Right? So I want to get from a closeness of numbers, you know, the Wehrl entropy, that's a number that you can compute. It's, I don't know, 1.01, to, that's a closeness of numbers. How close is 1.01 to 1, to a closeness in the state of space, in this infinite dimensional space. And actually, the theorem, here is this, it's also last year, is yes, you have such an inequality. Actually, in this general framework of general concave function f, but think of it as x log x, right? So this, if this thing, the left side, is close to this first term on the right side, then it says that this thing here is small. So this means the trace of the absolute value of rho to a coherent state is small. Okay? There are things to be remarked here. First of all, it's a trace norm distance. That's the natural and optimal distance in which you want to measure the distance of a state to another state. Number two, there's a power 2 here, which is sort of natural when you're at a minimum, right? So you think, I mean, a typical minimum is a quadratic minimum. So it's natural that the distance from the coherent state is controlled in terms of this power. Okay, and so this ties in with developments that have happened in mathematics in the last years, where people have thought about stability of functional inequalities. Again, one of the paradigmatic points being this isoparametric inequality. If your quotient of the area to the squared of the length of the boundary is almost minimal, is your set close to a disk? Okay, and so this, in the last 10 years, this has been a big topic, and so we are working in this vein. Anyway, so let's move on. This was what I had to tell you concerning Glauber coherent states. Now let's talk about different coherent states. Let's go to the sphere, okay, to Bloch coherent states. Okay, so we have a spin J representation of SUN. Okay, we have 3 generators, S1, S2, S3, and then we know that the eigenvalues of S3, they run between -j and j. And so we pick an eigenvector corresponding to -j. All right, and now we rotate the axis, and so for every we parameterize by these points omega on the sphere, and we pick a different eigenvector for each omega, and this gives us these Bloch coherent states. Okay, good. And now we do the same thing. We take now a quantum state. We look at expectations in these coherent states. So these are functions now parameterized on the 2-sphere. We take the classical entropy, just the rho log rho, but now rho is the given, right? I mean, what I'm saying is this expectation omega rho omega, that's now a probability density on the sphere. Now we take the rho log rho of that thing, or more generally a concave function. Again, the statement is this is minimal for Bloch coherent states themselves. Okay, it's the same thing that happened for the Glauber coherent state. That thing was conjectured by Lieb in 1978, immediately when he solved this Wehrl problem. A first proof of this, you know, I mean, this came 40 years later, and people were heavily working on this. There have been many partial results in between, but it really took them a long time to settle this. And so the new contribution of this result from last year is that the equality cases are settled. So again, you are minimal only if you are a coherent state. And what's also interesting is that I was telling you, you know, I mean, Lieb used these very deep theorems that I mentioned before. Then, in 40 years of work, Lieb and Soloway could prove this using a certain technique. Now, the proof that I'm giving in this paper is essentially the same one that I gave for the Glauber coherent states case, except that I'm using the isoparametric inequality on the sphere. Right? So you have a set now on the sphere. It has a certain area, and this boundary has a certain length. And now you ask yourself, among all sets that have a given area, all subsets of the sphere that have a given area, which one has the shortest boundary length? And again, that thing is enough to deal with that, and it completely proves that theorem. Okay, good. So where are we? And what do we want to talk about next? So what I was telling you is 2 different theorems, 2 different families of coherent states, and we got classical probability densities, computed their classical entropies, and were minimizing those. And the results in both cases were very similar, right? I mean, what came out were the coherent states themselves. So this somehow smells like there should be a general theorem, right? It smells like this should not have anything to do with Glauber coherent states on R2 with P's and Q's, or Bloch coherent states with omegas. So what is this general theorem? And I don't know. I mean, this is sort of the end of the talk where I'm presenting results. What I'm telling you now are questions. And so here's a general setup, how you could imagine this. Okay, so you're given a Hilbert space, H, and a group that acts on that Hilbert space, a representation. Okay, now you fix a unit vector on that space, in that Hilbert space. And now you move that fixed vector around by your group representation. Okay, that gives you a family of states. They're parameterized by these group elements. Now, abstract group theory, nothing deep, tells you that you have this over-completeness relation. Okay? So again, you can think of these things as coherent states. They have exactly these properties that you had before. They are over-complete, but they resolve the identity. So again, we can look at a classical probability density, this expectation value of rho in these coherent states. They're now parameterized by the group. We can take rho log rho of this gadget and ask ourselves, what minimizes this? This is the generalization of this Wehrl problem that I've told you now in two different cases. And one thing that we should remember is that this construction of coherent states depends on the choice of a basic vector. So if we go back, right, there was for the Glauber coherent state, we chose the Gaussian. I mean, why did we choose the Gaussian? Well, I guess because everybody chooses the Gaussian, but I mean, that's not really a satisfactory reason. Then the other thing for the Bloch coherent states, well, we chose the eigenvector of S3, the minus j, and the lowest eigenvalue of that. Why did we choose it? Once again, because everybody does it, but why really? And so what this question that I'm asking here, this problem might shine a light on is, what are good vectors to base coherent states on? Right? So I mean, if you are in such a setup, I mean, there might be a good way of choosing the coherent state, a good way of choosing the psi star vector, and a bad way. And I'm trying to find which ones are the good ones and which ones are the bad ones, and having this sort of Wehrl entropy minimized at coherent states might be a way to distinguishing when coherent states are good coherent states. Now, I've told you, so what I was telling you, you didn't see a group probably because this R2 is not really a group and S2 is also not a group, but really there was a Heisenberg group hiding in the background. That's sort of because translations and modulations don't commute these operators, so therefore there's a way to enhance this to make a group out of it, and this becomes the Heisenberg group. But this is really the Heisenberg thing. And the Bloch coherent states, that's really the SU2 thing. So therefore what I was telling you before falls in this setup. Now there are other results, but very few. There's the SU11, I don't know whether you know what that is, so it's 2x2 matrices, but now it's a non-compact thing. It's sort of, SU2 is something like a sphere, and SU11 is something like a hyperbolic space, okay? There's something else, an aX+b group. These are there, the analogous theorems are known, and then for very few special cases of SUN, corresponding theorems are known. But in general, this question is open. And I would like to advertise this to you. It might have something to do with representation theory. In representation theory, you have the notion of a so-called highest weight vector. And that might be a good thing to discuss coherent states. And I should also mention works by Perelomov, Konstant Sternberg, Barry Simon, Lisinski, and many others who sort of thought about what is a good way of building coherent states, but these things were not really conclusive, I would say, and these did not focus on this Wehrl entropy. So the new idea here is to use this entropy criterion as a criterion to distinguish one set of coherent states from another set. Let me skip over this. I'm trying to explain you here how this thing fits into the group picture. And let me instead tell you about a recent theorem by De Palma, some 5 years ago that I would like to understand. This again, this is an open problem, something that I don't know. Namely, what you can do is, well, let's again, this is our Wehrl entropy, we know that. Okay. Now rho is the state. Now let's not minimize over all states rho, but let's minimize only over those states that have a previously assigned von Neumann entropy. Okay, so I give you a value little s, and you minimize this over all states with this given von Neumann entropy. What's the answer then? Right? I mean, then you prevent these coherent states coming out because obviously they're rank 1, they only have entropy 0. So what is the answer there? And that actually, De Palma found that, and the answer is Gaussian thermal states. Okay? I think this is quite remarkable. This is, again, a very deep theorem. I mean, this is decades of work of Holevo, De Palma, Trevisan, Giovannetti, and others on what's called the Gaussian optimizer conjecture. For those of you who work in this business, this is, I mean, one of the big things about Gaussian channels, where you would like to have a general theorem, and this is in general not known, but some partial progress was enough to solve that thing. This thing is, for instance, not known. The analogous thing is not known if you have more than 1 degree of freedom. If your P and Q are multidimensional, then this is not known. And now we can go further. What is the analogous theorem for the Bloch coherent states? Okay, so try to minimize this Wehrl entropy for a given spin J representation when you have a given entropy. What would be the optimal state? Right? I mean, here, sort of the funny thing is Gaussian thermal states come out. So this sort of, the problem itself creates the harmonic oscillator. The problem creates the Hamiltonian. There's nothing in the setting of the problem that puts in the Hamiltonian. I mean, we have sort of the Gaussian that we use to build the coherent states, but then out comes the Hamiltonian from nothing. From one state gives me the full Hamiltonian. I think that's remarkable. And I don't know what the analogous result would be for the Bloch coherent states. And even further away is a question for general groups. What do we have there? The only thing in joint work with Eric Collin, well, we have always this, for general representations, we have this inequality that the Wehrl entropy is always greater or equal than the von Neumann entropy. Now, sometimes this inequality is saturated for a given value of this S. We can give you a couple of non-trivial examples. That's when we don't get a Hamiltonian out. That's sort of the trivial case. But that's all we understand for the moment. And with that, I want to conclude. So to summarize, I have explained to you a minimization problem. You start with coherent states, you produce a classical function, compute its classical entropy, and optimize, and you get coherent states out. That's something that says that these are good coherent states. I want to ask you, in general, given some group representations, is the same true, at least for some coherent states? Or can you give me of coherent states where it's not true? And then there are various versions of this problem. In particular, one version is this last one here, where you do the same minimization under a given von Neumann entropy. And I think those would be interesting results. They're certainly mathematically interesting, so the things that have been going on, I've not talked at all about proofs, but I think they're interesting on different levels. They bring together different mathematics. There's some complex analysis, there's some calculus variations, some geometric measure theory, and there's this representation theory, all going into this. If you are interested in this, have a look at the papers. But I also hope that besides its mathematical interest, this perhaps really says something what we want from a system of coherent states. And with that, I thank you for your attention. Thank you.
Any questions?
Yes. So maybe the answer was hidden somewhere in the talk, but regarding the standard Wehrl entropy that you started with, you wrote this bound this strict bound between the Wehrl entropy and the von Neumann entropy.
Yes.
Can it get arbitrarily tight?
That is sort of this question, this last question that De Palma asks. So it's exactly, so it's a strict inequality, and yes, in an asymptotic regime it can get tight, but it can also get away from each other. And so the last question is exactly to study the tightness of this. So exactly fixing the von Neumann entropy, how small or how close to it can the Wehrl entropy be? That's
okay,
exactly
so it's the question what the minimizer is answered.
Yes.
But then the minimal values.
Okay, now right. So I only gave you the answer. So the answer was the minimizer is a thermal state. So now you take it's a thermal state of the harmonic oscillator, right? So you take this, you compute its entropy, and then you can get an analytic expression, and you can compare that with the trivial lower bound. And so you can really check the tightness of that bound. I just didn't bother writing it up. But thanks for pointing that out.
Thanks.
Yes. Thank you.
You want to try?
At the beginning of your talk, you mentioned that your proof of this initial version of the theorem with, that is much simpler than the one that Lieb and Solerev, I think, found. Is there a way to indicate in which sense it's simpler without becoming technical?
I mean, this Lieb's proof is based on two inequalities. They're called, I mean, one is called the Hausdorff-Young inequality. So let's talk about this for a moment. So we have the Fourier transform, and the Fourier transform is an isometry in L2. And it's trivial to see that there's a bound that if you have a function that's absolutely integral, then the Fourier transform is bounded. Now, there is something in between these two statements that I just made. And that's this hard thing that's called the Hausdorff-Young inequality that has Gaussian optimizers, but to prove that, I mean, this is pages and pages of computation, and or I mean, also clever ideas. And I think there is no really intuitive understanding. I'm not saying that my proof here sort of is intuitive, but at least I think it's the only thing that I need from mathematics, I mean more than really basic elementary mathematics, is this isoparametric inequality. Whereas for this Lieb's proof, you really have to go through this proof of this Hausdorff-Young inequality, plus another thing that's called Young's inequality. And I mean, this is... I mean, this, I don't know how to measure its complexity, but probably I would need 2 weeks in class to sort of teach these things. It's just very, very deep. It's beautiful. I mean, it's very nice, and it's beautiful that they did this, and that you know that you have 2 bounds, and that you can concatenate 2 bounds and still get something sharp. I mean, it's ingenious, but sort of it seems like there's a direct way that bypasses all these difficulties. I don't know whether this is an explanation. I should say that this other proof on the Bloch case, that is more quantum information theory based. There they have channels. They go from spin j to spin j+1 in a clever way and do something that's perhaps a little bit more intuitive. So in order to prove the spin j inequality, they first go from spin j to j+1, then from j+2, and so they have a chain of inequalities, and then they say that in the high spin limit, one is sort of in a semi-classical regime, and one arrives at a classical problem. So that, I would say, is an intuitive proof. But again, it's long, it's not really elementary.
Here. So I'm not sure if I understood the connection with the minimal output entropy of a Gaussian channel.
Yes.
So you mentioned some results related to this problem, then you want to minimize the Wehrl entropy, and so what is the connection between these two problems?
So I mean, one one thing is, I guess this whole thing is a Gaussian channel. I mean, it's a quantum classical channel. So we go from states to probability densities. So that's a particular thing. So now there have been these works by Holevo and others who have Gaussian channels and sort of who start with a general state, then they apply a Gaussian channel, and then they want to say that if you optimize, now it's a quantum channel, now if you optimize the output entropy given the input entropy, then your input entropy wants to be a Gaussian state. Okay, and so they can do this in a certain limited number of cases. But they can do it sort of for one family of channels. And this De Palma's idea to solve this latter problem here is that he does a clever limit where this channel, for which the Holevo stuff applies, sort of becomes a classical channel. And so therefore, from the quantum result, they can deduce something about this quantum to classical channel in the limit. But that is sort of restricted to these particular cases for which the Holevo stuff applies, and that is only one mode. So they cannot deal with two-mode or multi-mode bosonic channels.
So this is it's a quantum to classical channel, it's a Gaussian channel,
limit,
and therefore you can use the result. I see.
Exactly,
okay.
yes.
Thanks.
Thank you.
Okay, if there isn't any question, let's thank Rupert again.
Thank you.